Welcome to the first of the Natural Science and Mathematics Colloquia for this year. We have a very exciting lineup of talks. I'm first going to introduce President Jordan, who's going to say a few words.
One thing you have to love is the efficiency of a physicist, right? Mince no words. I said, I think I need an introduction. He says, okay, fine. Here's President Jordan. There you go. I love it. What a beautiful day to be in Southern Maryland. It's a glorious beginning to a new era for our Natural Science and Mathematics Colloquium, an era in which we have a committed local sponsor, and we're just really thankful for KBR Wiley for making the colloquium possible this year. Welcome, everyone. Thank you for joining us for the first in a series of important, thought-provoking speakers this semester. Reading the bios of our diverse lineup of panelists, I have no doubt we will have engaging and stimulating conversations about the art of communicating science and mathematics. How can we take the complexities of the molecules and phenomena, equations and processes we study with intense enthusiasm to the everyday Jose and Tawanda and Bill and Ahmed and Terry, and talk about our passion to them in such a way that they not only feel our excitement, but actually understand what it is that we're talking about. Years ago, when I was perfectly happy living my life as a professor and a biochemist, I would tell my students that the true sign of an educated person is not your ability to use big words to describe a complex phenomenon, but rather your ability to explain whatever it is that you're working on to anyone on their level and have them understand it. And so I am very happy that we began this year's colloquium discussing how to communicate science and mathematics. I'm a strong supporter of colloquia like the NSNM, the coming together of bright minds, regardless of your area of expertise, to learn about the latest discoveries and innovations in science and mathematics in an unpretentious setting. Since its inception in 1998 as a grassroots initiative by the science departments of the college, the colloquium has hosted over 200 speakers here on campus, including 2 Nobel laureates, a MacArthur Award winner, TED speakers, and other leaders in the sciences. All of these lectures are free and open to the campus and the community. Support from KBR Wiley, especially the generous support of Peter Green, enables St. Mary's College to enhance these conversations about new developments in science and mathematics. Pete Green is the president of KBR Wiley Aerospace Group, a member of the St. Mary's Foundation Board, a friend and an ambassador of our college. Thank you, Pete. Welcome, KBR Wiley staff? Employees, how about that? That's a good word. And now, without further ado, I invite Pete Green to the podium. Thank you all for coming, and I hope you enjoy the evening.
So do you guys like staff? Okay. Yeah, maybe we'll hang with that. So Tawanda, thank you very much. Thanks for the kind words. It's a privilege to be here. My name is Pete Green, and I have the honor to lead KBR Wiley's Aerospace Group, as Tawanda already mentioned. We are headquartered here in Southern Maryland, but we have 24 offices across the country. And in those offices, in other locations, we have over 1,500 people that come to work every day, working as scientists, engineers, subject matter experts, technicians, and they are providing technical solutions, trying to solve problems for our customers. So many of them come from a science background, and therefore we think that education is extremely, science education, mathematics education is a very important keystone, and it is also feeds into us, which is great for us. So big support of education, and especially we want to encourage students that have interest in science and math. Personally, I want to thank you for giving us an opportunity to support this colloquium, and I am looking forward to a conversation about how do you tell people about science and math. Communication is so important, and sometimes maybe you could explain something like a Green's theorem to me, because I didn't get that the first time. I barely got through that. So I look forward to hearing those things explained. Thank you.
It's not that I'm terse, it's just that I'm lousy at introductions. So, before we actually start our panel discussion, I would actually like to do two things. First of all, there are a lot of people that I would like to thank who made this possible tonight. I want to thank President Jordan and Peter Green for speaking, for talking with us today. I also want to thank KBR Wiley for the wonderful, generous donation, which has allowed us to really expand the scope of this series. It's made it possible to bring in a lot of speakers from from a lot of different places, and we hope to have a really super colloquium series for everyone this year. I also want to thank our panelists for coming tonight, and to Jerry for moderating the panel discussion. And there's also been a lot of work by a lot of people to put this together. Linda Jones, Peggy Aud, Lika Pristo, Lauren Sampson, and Kaylee Hauk did a lot of work towards making this. Kaylee Hauk in particular designed the poster for the colloquium series that you see up there. Ken O'Connell, Jacob Bartholow, Thomas Gallagher, and Jerome Burley for their help in setting everything up today for this, and also the Natural Science and Mathematics Colloquium Committee, Susan Goldstein, Daniel Chase, and Kevin Emerson for, again, their work in getting wonderful speakers. So thanks to all of you for all those people for doing it. Thanks to everyone here for coming to the colloquium tonight. I also would like, the second thing I want to do is actually mention a few of the upcoming lectures for this semester. Our next week's lecture is by Dr. Michael Mann from Penn State University. Mike is one of the top climatologists in the world. He was the principal author of the famous hockey stick curve paper, which was featured prominently in Al Gore's book, An Inconvenient Truth. His talk is entitled The Madhouse Effect. It'll be here in Auerbach Auditorium at 6:30 p.m. next Wednesday, September 21st. Mike's a great speaker. One thing I should mention is that how many people out there are fans of Randall Munroe's webcomic XKCD? So, all right. If you saw Monday's webcomic, Randall Munroe actually consulted with Mike Mann, next week's speaker, on getting that comic accurate. There's going to be a book signing after next week's talk of his new book, which actually, by the way, has not yet been published. So, in fact, you'll have a chance to actually purchase advanced copies of it before the actual publication date. On Wednesday, September 28th at 4:40 p.m. in Schaefer Hall 106, we're going to have Dr. David Perry from the NSA giving a talk called The Coming of Enigma. On Wednesday, November 9th at 4:40 p.m. in Schaefer Hall 106, we have our own alum, Dr. Amanda Perry of the Virginia Department of Forensic Science, discussing current trends in forensic chemistry. The final lecture of the semester is one I'm very excited about, Thursday, November 17th at 6:30 p.m. in St. Mary's Hall. It's a really fun talk. Dr. Eric Spana of Duke University will speak on Harry Potter and the Wizarding Gene. I've seen the talk. It's fantastic. We're actually doing it the day before the new J.K. Rowling movie, Fantastic Beasts and Where to Find Them, comes out. And so it's a wonderful talk. It is actually good for people of all ages. If you have kids who are interested in science, please think about bringing them to the talk then. He's a great lecturer. These are just some of the lectures we have for the next semester. You can see our complete schedule on the events calendar for St. Mary's College or our Facebook page. All of the lectures are free and open to anyone. All of them are meant for general audience. Okay, now today's event, Talking Science, How to Make the Point. Jerry?
Okay. My name is Jerry Gabriel, and I'm very pleased to be here to moderate our discussion today, this afternoon, whatever it is, this evening we'll call it. So I'm gonna introduce our folks here. We're gonna show a clip from each of their work. We're gonna have some conversation just among the three of them. I'm gonna ask them some questions, and then about halfway through, we're gonna open up the floor to you all. This is gonna work with roving mics. There's gonna be two, one on each side, so you'll just, when we get to that point, it'll be obvious, and you can raise your hand. So, I think that's the important thing. So, our panelists today, the far end here, our very own Dave Kung. St. Mary's College of Maryland Professor of Mathematics Dave Kung completed 3 degrees from the University of Wisconsin-Madison before joining the faculty at St. Mary's in 2001. Professor Kung has authored a variety of articles on topics in harmonic analysis and mathematics education, and is the recipient of numerous awards, including the 2006 Teaching Award from the Maryland, Virginia, DC section of the Mathematics Association of America. Professor Kung's great courses, lectures, How Music and Mathematics Relate, have become a top math and science seller for the teaching company. On the heels of that success, he has since recorded a second series of lectures, Mind-Bending Math, Riddles and Paradoxes. He is also co-writing currently, right, a book about college math teaching entitled, What Could They Possibly Be Thinking? Understanding Your College Math Students. Dave Kung. Next to Dave is Evelyn Lamb, who earned her PhD in mathematics from Rice University in 2012. After graduation, she received a mass media fellowship from the American Association for the Advancement of Science. This set her on the path of writing about mathematics for a general audience, and out of the experience was born her blog, Roots of Unity, which is hosted on the Scientific American Blog Network. Her work has also appeared in Slate and Nature News, and she co-authors the American Mathematical Society's blog on math blogs, a tour of the mathematical blogosphere. Evelyn is passionate about communicating the beauty and power of mathematics, and she lives in Salt Lake City. And finally, next to me is Mark Levinson. Before embarking on a career in film, Mark Levinson earned a doctoral degree in particle physics from the University of California, Berkeley. In the film world, he became a specialist in the post-production writing and recording of dialogue known as ADR, automated dialogue replacement. He has worked closely with such directors as Anthony Minghella, Francis Ford Coppola, and David Fincher, and on such films and TV shows as Seven, The English Patient, The Talented Mr. Ripley, Cold Mountain, and House of Cards. Getting back to physics, he is the director of Particle Fever, a 2013 documentary film tracking the first round of experiments at the Large Hadron Collider near Geneva. The film follows the experimental physicists at CERN, the European Organization for Nuclear Research, who run the experiments, as well as the theoretical physicists who attempt to provide a conceptual framework for the LHC's results. The film begins in 2008 with the first firing of the LHC and concludes in 2012 with the successful identification of the Higgs boson. We can get into that later. He is also the writer, producer, director of the narrative feature film Prisoner of Time, which examined the lives of former Russian dissident artists after the collapse of the Soviet Union. Currently, he is working on a film adaptation of Richard Powers' novel, The Goldbug Variations. All right. So we will just jump right in. Oh, we have clips for you first. We will not jump right in.
We'll not jump right in.
First, a trailer from the Partner feature.
Don't hit that.
Thank you all. Thank you for your attention. Thanks to everybody on the panel. If I could just ask you all to remain seated just for a few minutes.
In exploration, there needs to be the set of people who have no rules, and they are going into the frontier. I've never heard of a moment in history where an entire field is hinging on a single event. The Large Hadron Collider, the biggest machine ever built, is finally going to turn on.
You take two things and you smash them together. You get a lot of stuff out of that collision and you try to understand that stuff.
Could be nothing other than just understanding everything.
Little did I know when I started that the experiments would take 30 years, and here I am still not knowing. I really want to know the truth.
The first time I ever saw it, I can remember walking in and just being stunned, like, 5 stories completely filled with custom designed, hand-soldered microelectronics.
There are 10,000 people, over 100 nationalities. 100,000 computers deal with the data. In fact, the World Wide Web was invented at CERN so that physicists could share the data.
This is really my generation's only shot.
Let's get started, everybody. Now comes the day of reckoning.
Given the complexity, they're already about a week or two behind.
We're saying that all their tools are breaking.
It begs the question, what are the risks?
It would be a catastrophe for physics. This helium leak, really frustrating.
You've got magnets sheared off their jack. Completely catastrophic.
We're at a fork in the road, and it's cranking up the suspense as much as it possibly can.
We may discover additional space dimension, the mystery and the origin of the universe.
We may be at the end of the road.
The entire control room is like a group of 6-year-olds whose birthday is next week.
It's incredible that it's happened in my lifetime.
Whatever we learn is going to have a dramatic impact on the way human beings think about the universe forever.
A bit more stationary.
Yeah.
Yeah.
I have to ask you a question about that one.
Mm-hmm. That one was based on an Onion article.
Oh, cool.
On a what article?
An article from The Onion.
Infinity. Most people think it's just one thing. It turns out there are different sizes of infinity. We're going to look at the groundbreaking work of German mathematician Georg Cantor, who was born in 1845. Cantor was the man who tamed infinity. His work was groundbreaking and at the time very controversial. Top mathematicians in his time, they thought, well, Kronecker thought he was a scientific charlatan, a corrupter of youth. He was a rival of Cantor's, in case you couldn't tell. Poincaré said about Cantor's ideas, they were a grave disease, a grave mathematical malady, a perverse pathological illness that will one day be cured. On the other hand, not everyone was so negative. Bertrand Russell said, one of the greatest intellects of the 19th century. Hilbert said in German, aus dem Paradies, das Cantor uns geschaffen, soll uns niemand vertreiben können. No one shall expel us from the paradise which Cantor has created. Here's a similar problem, tying a knot in a rope. The question here is, can you grab the ends of the rope and then tie it into a knot somehow without letting go? And if you try this at home, you'll quickly find that you think it's just not possible. But I have two solutions for you. One's mathematical and one's magical. Let's try the magical one. So I'm grabbing the rope and I'll just sort of do something like this, and I just say there's a knot that's just going to appear in the middle. Oh, let me try that one more time. So I wind it around or something like that. And oh, look, there's the knot. So that's the magician's way. Mathematicians have a different way of solving this puzzle, and the way to do that is
Oh.
Good? Okay. We may get more of that later. All right. Great. Well, Evelyn, I'm going to start with you. You mentioned a minute ago that post, that article was based on an Onion article, an article in the newspaper The Onion, the facetious newspaper The Onion. And my general question is, where do, and this eventually will be for everybody, but where do your ideas come from? I'm working right now with a student on a senior project. We're sitting in my office and we're doing a lot of thinking about, like, where do the ideas come from? Do I go and do I look at science journals? Do I step back and ask what are the big questions and go from there? Where do you start?
Yeah, well, I wish I knew that. But I mean, every once in a while you get really lucky, and The Onion has a satirical article saying that the nation's math teachers made up all these new trig functions, and then it turns out one of your friends mentions these old trig functions that people used to use and don't anymore because we have calculators that work a lot better, and so you can kind of tie this in. But that doesn't happen all the time. That's a special thing. But some of it is, if big news happens in math, if somebody solved the Riemann hypothesis, I would be on that.
Right.
And something like that. So that's definitely a source. But sometimes it comes from talking with people I know who aren't mathematicians, and they'll, something will come up and they wonder about something, and you realize, okay, Had got a metaphor for this that might be helpful if someone wanted to know about that. Or I was on a hike recently, and we had done a hard hike the day before. It was a little harder than we thought. I had some blisters forming, and I felt like I really understood Zeno's paradox in a way I hadn't before. So this is the paradox that says that motion is impossible because to get from here to there, first you have to go half the distance, and then you have to go half the remaining distance. And I kept obsessively looking at my GPS, and it kept saying, you've gone 0.2 miles. And I thought, to get there, I have to go half the way, and half the way that's left. And I didn't know if I would make it. I felt like, that's an idea
what he meant.
Yeah,
he was on a hike.
Suddenly, he must have been hiking in the Tetons and came up with this idea. But yeah, it kind of comes from all over for me. Sometimes it's things that I have seen in math that I just think are beautiful, and I'd like to see if there's a way I can share those with people who aren't in grad school in math or haven't had that experience. So it's a wide variety for me.
Okay. Either of you, Mark and I were talking about this idea a little bit earlier. You're working on a new movie about a book. Do you care to talk about that and how that idea came about?
Yeah, I can. I mean, it's a little different from me, I think, in terms of my primary interest is not trying to specifically talk about science, but I happen to have a basic science background, and I think and this gets to your question even more directly, I mean, what motivates me is finding a good story. And I think that is the principal interest, and maybe the most important thing in terms of communicating science, I think, in terms of what engages. And so particle fever, once I left physics, I actually was just in the fiction world for many years and really did nothing, didn't know documentaries, did nothing that really was about science. These were completely unrelated projects. When I heard about this project, when I heard how it started was actually a physicist was trying to make a documentary, and I heard that this guy was trying to make this documentary and had done one interview and had no audio and nothing was happening. And what I realized though was it's a good story, that it could be. I knew enough about the situation that I knew that when this thing turned on, there was a lot at stake, and there was a lot of possible human drama. People had spent their lives doing this, and it could be an interesting and dramatic story. And it ended up being more dramatic than I expected, but that's what drew me to it. And the project that you mentioned now is another story that is really good. This really is a fiction story. The novel is the Goldbug Variations, but again, it's a tremendously compelling story. And what I do like is that it does integrate sort of ideas about science and life and art. And that is a passion of mine, is looking at the overlap of those two things.
Okay.
And I love Mark's reference to story and that being core. I really feel like when it comes to trying to communicate math, especially, but math and science in general, I feel like I have just two tools, and one is storytelling. And so, you saw in the clip, like telling a story about Cantor and how controversial his work was. And that's one of my tools, and the other is just to surprise people, right? And to set that up where here's one way to tie. I can do a little sleight of hand and act like I'm tying a knot in the rope. But if I tell you that it's possible, I told you in a matter of 30 seconds, I said it was impossible, but I'm going to do it for you now twice. And setting up that sort of surprise gets you to the point, like is everybody wondering how you do it the other way, right?
Yeah.
So I mean, that's sort of what this idea of surprise is incredibly important to me, and that's my other tool, and I feel like that's about all I've got.
Okay, good. Well, I wanted to talk to you about storytelling, and I'd just like to hear you and all of you really talk more about how what that process is, how you go about looking at these relatively abstract things, or mundane things, work in a lab in your case, and find and pull the story out of that. Where does that come from? What are your tools other than surprise?
Yeah, I feel like there's, I feel like looking for a story is a difficult thing and finding it, but I think there's, especially when you're talking about science and math communication, there's a real tension between human nature and how we evolved to understand stories. And so you have to communicate through stories because of that. On the other hand, I think that there's an element of mathematics and sciences which fundamentally is about overcoming that. Science itself is about overcoming the idea that anecdote is good enough, right? That we have to go for more. We have to, we need reproducibility. It's not just, my friend did this one time and that was crazy. It's, will that happen every time? Under which conditions will it happen? All of those. And so science and math tend to be this sort of almost monotonous process of digging in and rejecting story, rejecting anecdote in favor of this really detailed critical thinking. And so there's this tension between rejecting stories on one hand to do the science and finding stories to tell when you're trying to communicate that science. And I think it's one of the real challenges of doing science communication. But I think that the particle fever is a fantastic example of finding not just one story, there's the overarching story, but finding sub-stories, subplots in there that sort of get you all in the service of understanding a little bit more of sort of the groundbreaking physics that's going on. And that physics itself is not at all about stories.
Yeah, that's interesting.
I mean, I think sometimes when I'm writing, I feel like I'm not really writing about math as much as writing about what it feels like to be a mathematician, and kind of I try to, even if the thing that you're writing about is not a story, you can talk about your own emotional reaction to it, or the reaction of the mathematician who you're writing about, or something like that. There's actually a book written recently called Birth of a Theorem by Cedric Villani, and this was a very odd book. I enjoyed it quite a bit. He's a Fields medalist who's somewhat famous. He's been called the Lady Gaga of math, which I think is not a terribly accurate description, but he is famous for dressing rather flamboyantly. No meat dresses, it's more along the line of like 19th century type of thing, cravats and these brooches and stuff like that. He stands out at a math conference where we are both overdressed currently. But he put a lot of just emails between him and his collaborator in there. So there are a lot of dry details that, like, if you aren't studying statistical physics, this isn't something you are going to understand. But in there you see he's writing about his emotions related to this, and I think it really gives you an insight, even if you end the book not knowing even what the problem is that he studies, you have an idea of why he could be so passionate about this and how he feels when he does this. So that's something I try to communicate is, why do I feel surprised, or why do I feel disappointed by this, or
capitalizing on your subjectivity as somebody who does this and understands it. Yeah, that's interesting. Okay.
I think, just expanding on it, and both of them touching on it, what you see is, story is fundamentally about humans. That's the bottom line. Yeah. And, an equation itself doesn't have a story. What Dave was showing, Cantor's infinity, what makes the story is the people and the conflicts and other things like that. And Evelyn saying that, showing what it's like to be doing mathematics, again, the story is coming from the human side, and so I think that it's about finding the human drama behind it that can reveal it. And that's the important thing, I think, that we all want to communicate. The science itself, the reason I think it's often considered dry is because it's divorced from that. And you see it in a textbook, or you even just see something in a newspaper and it just says this is a theory. But what's dramatic is how it was found. I mean, Monica, the young postdoc in particle fever, at one point I remember she said, you know, they've been working for years and years and it was this dramatic thing, and you know, 20 years from now it's going to be a line in a textbook, you know, they discovered the Higgs boson, you know. And that's, I think, the important thing. And in particle fever, I mean, it's interesting, I'm glad that you like the story, and there is a story. I had no idea there was going to be a story in terms of what it really ended up being, because when I started, we didn't know if there was going to be a discovery. And so I was thinking in terms of very classical ideas about what makes a good story. And, you know, there's very classical things of, you know, conflict and tension and anticipation and development and, you know, characters. And so I had all sorts of ideas of what it might be because I couldn't count on a discovery. But I thought, I did have a story because I had humans, and I knew that there were stories about them competing with each other. There were stories about the difference between experimentalists and theorists, which most people outside of science don't even know that exists, but it's a very dramatic story. I thought there was, you know, so I had imagined all these things, and then you know, especially with a documentary, it's not something you're really directing too much in terms of plotting the story. Luckily, as things happened, I could see the story that was emerging, and it meant throwing out a lot of other things and then, you know, laser beaming on what ended up happening.
Okay, yeah, that's very interesting. So you all noticed during the clip of particle fever, well, to backtrack, I think a lot of science writing works by analogy, and you mentioned a minute ago metaphor. And Mark, I wanted to ask you, when you were making particle fever and you were dealing with these concepts, and how can you kind of take us through the process of trying to represent these things? So you've got the human dramas, the human stories, but then you've got the actual physics that you've got to get across to the reader. And there's always that section, you know, in science writing where you've got to like roll up your sleeves and convey, get this across to the reader or the viewer, how this thing actually works. And I wonder if you could talk about your process, because I think it's really fantastic. Some of the kind of I won't say tricks, but some of the tools that you pulled out of your hat there. Can you talk about that?
Yeah, well, I mean, ultimately that issue of integrating the science was probably the hardest part in finally putting the film together. But the way we tackled it was we avoided it till the last. I mean, I wouldn't say avoided it, but we pushed it off. And so we focused in the filmmaking on getting the dramatic story right. And I ended up having this fantastic editor, Walter Murch, who I had worked with for, you know, on many other films, On the English Patient, Talented Mr. Ripley, and things like that. And Walter and I had worked together. Neither of us had done a documentary. And so our approach was, let's get the story structure down in terms of the characters, in terms of the drama, where we're going. And we will go back and we will insert the science where we need it. And our mantra was just enough, just in time. So the other thing I wanted to do was I wanted to integrate it as seamlessly as possible, so that there was not that sense in which we had to stop the dramatic narrative to explain science, because I think that also was sort of would have been deadly. I mean, you know, and so it was a very delicate balance of, you know, when can we interrupt it? I mean, you really you nailed it right there. Is how do we insert it in a way that is not distracting and you still are emotionally engaged? And so we did use a number of tricks in some sense. One of them was that I did not want an omniscient narrator. I mean, just somebody that nobody knows who they are, just explaining the science. That was clear right from the beginning. And I also wanted it as much as possible to come organically out of the story and out of what was happening. And so the first trick was near the beginning of the film, David Kaplan, who was my partner and who was the one who originally, you know, wanted to make this film. He is giving a lecture at the Aspen Institute, and he really was giving a lecture. Now, obviously, we didn't just film his lecture and say, oh, here's our film. But there were some very good parts to it. And so we realized we could use that and use the tricks of filmmaking so we can cut away and we could change the dialogue, and because it would be natural for him to be showing slides, well, we could show animations. And so we could sort of slip in this basic explanation of what was going into a lecture where you felt you were there and where he was very funny and there's an engaging activity and things like that. And so that's what we always looked for. So we sort of looked for the places, first of all in terms of story development, where people needed to know something to understand it, and then how to actually insert something to convey that. And the other thing was, we realized one of the elements of the film is that we gave the characters these little home video cameras. We call them blog cameras. So they just had these little home HDV cameras. And the idea initially was that they would use these to film themselves when I wasn't around, if something happened, like a wedding. But what I also realized is that it became a way to tell the science, because it, especially Monica, who did this, who would do this, instead of a lecture or something in other contexts, I could just have her talk directly to the camera, and it felt like she was talking right to you.
Yeah.
And so we would sort of use this at critical points to sort of explain that it was almost like they're diaristic, that they're saying something like that. And so again, it was a way we used to try to insert educational parts without you feeling like it is, because you're watching Monica and you say, oh yeah, Monica, yeah, that says okay. Yeah. Oh yeah, she just said something important. Maybe I should remember that as well.
Hers have almost like a space station, like like the last stranded scientist on the space station feel. It's kind of cool,
right?
Because she's speaking right to the camera there.
Yeah,
that's great.
Sometimes with me on Skype at the other end.
Yeah, that's what I figured. Yeah,
but almost. Like that, yeah. So anyway, so that was I think that was the key actually, and then bringing in the animation to really pull it all together.
Right. Yes, that's really successful. I think the animation.
Coming at this,
jump in.
Coming at this from the academic perspective, there's an important moment when you realize the following. Like when we're teaching our classes, when some of you are sitting in front of us, like they're unlikely to just get up and all leave.
You never had that happen?
Unlikely. But when you're putting something out there, when you're putting a movie out there that's on Netflix, when you're putting these videos out there that I don't know, when you're writing, you're actually competing with everything else that's available to them. You're competing with another podcast, another film on Netflix. Yeah. You're competing with them talking to their spouse, doing the dishes, cooking, whatever it is. And so all of a sudden, what I realize is one of the things we do in our classes, I think is really, really poor, is we answer lots of questions that our students don't yet have. We just put the answers out there without helping students understand what the questions are so that they care about the answer, and then helping them understand the answers. But when you're doing this sort of work, you really have to get a hook into your audience. We have to get with a story, with a surprise, with something, so that they care, so that they're willing to continue on with that as opposed to flipping the channel. And then you can get into some of the more gritty details. You have to get them to want to know, and then that gives you a little bit of license to go and do some of the nitty gritty details.
Mm-hmm. Yeah, that was something that was hard for me coming from academia and starting to write, is that nobody has to read what I write. It is required for no one to read. And you have this captive audience in a class that you don't have when you're writing or creating something like that. I was talking with Dave earlier about this, about how I try to think of myself as being an entertainer more than an educator. What I want is for people to want to read what I'm writing, not an entertainer like a reality show or something like that, but just I want it to be something that's engaging, that someone is reading just because they want to, and not because I'm taking this real analysis class and I need to answer a question and I found this blog post that has the answer, which I hope doesn't happen too much. I worry about that occasionally. But yeah.
I mean, just to take off again on something that Dave said in terms of this idea of teaching what we think they need to know. I mean, I think something that anybody in this field, anybody that's doing something, science communication, and we all face is the problem of knowing what to leave out and what things to say. And I think that was the other big thing that we discovered. I mean, we sort of knew it, but really discovered in a dramatic way on Particle Fever, is you can't explain everything, and so we had to be we're very rigorous, and we said this is the lexicon of this film. And we're going to use these words, and we're going to explain these things, and we're not going to explain these things. And you can't be comprehensive, and I think that that's a problem that a lot of science communicators have, is they think they have to explain everything, and they don't explain anything. And so it's very hard to do that.
Or you lose the audience.
You lose the audience, and it's very hard. And it was something, I think, because David and I both had the physics background, we actually felt confident in saying what we're going to leave out. Anything that's in there is true, but there's a lot of things that are not there, and we just had to decide that. And so there's, and scientists have, nomenclature that it's, very arcane often and confusing even to them, and you have to really decide which of the words you're going to use. And in particle fever, for instance, there's this idea of the multiverse, but physicists say multiverse, anthropics, naturalism, environmental. We decided at a certain point, in particle fever, it's called the multiverse.
Period.
And that meant sometimes going back and re-recording with people, or dropping it, because they're not even clear with it. So to have all those words in it, you can't do it. And I think it takes a lot of discipline and to decide you're not going to do something because you feel incomplete. But it's a key to communicating.
Yeah, using jargon. When I'm writing, I try to see, like, can I write without using the jargony math words that are, people, especially with math, but other science as well, are very ready to be intimidated by what you're writing. And if it has a lot of jargon in it, it isn't. Sometimes you need the jargon because it's just really hard to avoid it. But, every time you use the jargon, think about, is this really a word I need, or can I use a different word that someone's going to be more familiar with to make this more accessible?
I mean, and in a sense, it's with a film, it's even harder because it just goes by.
Yeah, they can't look it up.
They can't look it up. I mean, I guess they could play it over and over again, but they don't usually. That's right. Yes. When it's written, at least somebody can stop and look at it, maybe look at something else. And we really have the problem. I mean, with a film, sometimes if a person hears a word that they don't understand, they just don't even hear the rest of the scene,
right?
Because they're still thinking, I think I know that word. I don't know what's he talking about, and then all of a sudden they realize it's gone. So you have to really be very careful about using a vocabulary that is accessible, actually.
Yeah. Okay. Yeah, Dave, do you want to jump in?
When you work for the Great Courses folks, they have a staff there that helps you work through some of those issues, which is really fantastic.
What kinds of things do they tell you?
Some of it is sort of working through the details, working through the jargon, deciding what to keep out. But one of their rules of thumb, which I think is really important, I think educators everywhere could learn something from this, is you have about 6 minutes to make a point. And after that, you have to move on. And so if you have, not all ideas fit into 6 minutes. And then, you have to split that up in some way. You can make some part of that point, and then there needs to be some sort of break, where you some break in the action, an animation, anything to sort of break that up, and then you can move on to another part of it. But you mean this idea, you have about 6 minutes to make a point.
Is that because that's how long their segments are, or because the way the brain works?
That's more about humans.
Okay.
Right, and you can all think about, like, how long our classes are.
And we've already been here much longer than 6 minutes.
We have.
Do we have a point?
On that note, I think maybe we'll shift gears and open up the floor to questions from out there, if there are any.
The person right in the middle.
Right, of course. Yeah.
There are two sets of microphones. Well, clearly to be involved in communicating your subject, you have to really know your subject well. But I was wondering if you could comment a little bit on what sort of other life experiences that you found that were really helpful in giving you the ability to communicate your subjects well.
So I am a musician as well, and I think writing is very different from performing because you get as much time as you want to sit there and have bad ideas and write really cruddy things before you can make it into something that's better. But I think music performance has influenced the way I communicate with people a lot, especially at a maybe not something like this as much where it's more spontaneous, but things where I'm giving a lecture or something like that. I've gotten a lot out of my experiences performing music. And also, I think when you're performing music, you are really communicating with someone else on an emotional level and trying to think about how you translate that emotional connection. How can you translate that into other media?
Exactly what she said.
I would say, well, for me, I really studied film. And so, you know, that really preceded doing particle fever or doing things that were really specifically about communicating science. And so again, what informed my approach to particle fever was my understanding of narrative films and the films that I really liked and understanding how they work dramatically. And so I think that is the thing that really, what I brought to it. In fact, when I got involved in particle fever, I said very clearly, I don't want to make a science documentary that's just going to explain all the physics. But if I can bring the narrative skills that I developed as a filmmaker, character, story, sound, all the tricks that we use to tell a story, that would be what I would like to do. And so I think that's what I would say. But also, the other thing that I think informs it that I've become even more aware of is the parallels between art and science. And it's something that I think people do have this sense that there's this division traditionally. You know, there's the left and the right brain. And you know, I think I approach it, for me, when I moved from physics to film, there was not a big dramatic difference because it's about creativity, it's about imagination, and those are the same in both processes. So I also sort of tried to look for those things, just you know, the aesthetics of it. I mean, I love the fact that both of them are involved in music too. You know, that I think that informs the way you look at things, because I think understanding art in general is not so different from understanding science. And you can use things about them. We look for patterns, symmetries. These are things that are parallel in all of them, and I think that's something that you look for, and I look for in my film and in science, actually.
And I'd like to build on that. I think that you know, all of the work I've done in mathematics, a significant portion is really just about problem solving, right? And about trying to look at a problem from a new direction, try to turn it around. And science communication, in some sense, is just about problem solving. It's just that you have different problems. Mm-hmm. Your problems are now about engaging an audience, about keeping their attention, about explaining it to somebody who doesn't understand the jargon, mm-hmm. finding metaphors that work. Mm-hmm. But it is sort of problem solving. I mean, in some sense, you know, science communication is sort of an ultimate example of the power of liberal arts, where you need to draw on things from this class, you need to draw on things from communication, from writing, from all these different aspects mm-hmm. in order to effectively communicate.
Well, and ultimately, you're using logic and discipline. I mean, you know, you may free associate in terms of coming up with an idea or something, but ultimately, as you say, what problem? How do you solve a problem? Well, we have certain ways we think, with certain logical things, and whether it's solving a mathematical problem or trying to write the right article and figure out what the sequence should be, or whether the sequence of scenes, it comes down to, you know, you have to, in the end, you have to apply a certain discipline to it, and that's similar in art and science.
Mm-hmm. That's great. All right. Another question? Yeah?
So as a group, you started out the discussion talking about the power of a story as a hook and as a communication tool, and particularly, you know, a human drama, in contrast to what Dave called like the mundane work or something like that. So when you focus on story, oftentimes one focuses on kind of individual agents. You know, it may be something like the lone genius who locks, you know, himself away in an attic for a few years, or if it's like on TV, it's a few hours, and, you know, comes up with some sort of revolutionary breakthrough, and that makes for a really good story, really good drama a lot of times, but it's problematic in a lot of different ways on the other hand. So one of them is inauthenticity, but the other part of it is there's actually been studies. There's a really interesting paper 2 years ago, I think in Science, where that showed that there's a really strong correlation between the extent to which scientific fields and other fields of study subscribe to the genius mindset, right? And if the fields that do this are much more likely to be less diverse, less inclusive. So, math, physics, philosophy, music, for example. And so there's, to some extent, that's a little bit problematic, or maybe more than a little bit problematic. And so I'd like to hear maybe just a little bit more about, dealing with that tension. Can we address this issue? Are there better ways? And I'll point to particle physics, actually, particle fever, as a good example, maybe, because there you had almost what you could call an ensemble cast, right? It was really a whole bunch of people. There weren't
10,000,
so much a
right?
single character. So I'll pass.
Particle fever is an interesting example of this, I think, both in its, because it is about science and because of what it does represent, which is huge collaboration. And so this idea of single genius, first of all, there's very, very few instances of anybody that really did just come out of the blue and come up with something that nobody else had been involved in. I mean, actually, the only thing I can think of is Ramanujan. So if anybody's seen this, there's this film out that came out recently called The Man Who Knew Infinity. And this man, this Indian peasant basically grew up completely isolated and really did come up with things. But almost everybody else is really working in a community. And I think one of the things that I loved about showing in particle fever is how collaborative it is. I mean, it's a model in some sense. Experimentalists, first of all, you have to, these are huge collaborations. There's nobody that understands any of these machines entirely. But I think the thing that's revealing is the theorists, because the theorists are the people that more typically are considered as these people that are these lone wolves that are sitting in a room with a paper and pencil, and they suddenly have this brilliant eureka moment that nobody thought of. And what you see is the theorists also really, they're in there, debating, and that really happens. They get very passionate, more than experimentalists in some sense. Now, ultimately, they do often. You have to go home and sit and think about it on your own. But that process of discussion is very critical, I think, to advancement. And so, I think there are people that have made taken huge steps, but I think that ultimately it is a collaborative process and has to be appreciated that way.
Yeah, I feel like these days the genius myth narrative is pushed more in fiction works, or I guess the bigger blockbuster type. The biopic, that's what I'm trying to say, biopic type things.
Of scientists.
Of scientists, yeah. So I'm thinking of, I'm blanking on the movie about Turing. There was also...
The Imitation Game.
Yeah, The Imitation Game about Alan Turing.
And The Theory of Everything, Stephen Hawking, yeah.
And those push that, but I feel like, because these things don't happen with one person sitting down and looking, in an attic, looking really panicked for a while and then suddenly getting it. Documentaries about these do portray this much larger cast. It is something I think about a lot in my writing is, what is someone who reads this going to get a message that math is not for them? It's only for these brilliant people over here. And I try to think a lot about, definitely say like these people had ideas, not trying to say that they didn't do something great, but how do you present that in a way that is inclusive and makes people feel like they're invited to come learn about it rather than, these really smart people did something that I'll never even be able to understand. And it's something, it's hard to do, but it is something I'm quite conscious of.
But it's true. I mean, raising The Imitation Game and Theory of Everything, it really gets to this point you were saying, is what does, the single genius story is a story that people write. I mean, it sort of takes the human thing to the extreme, and I think that's why people relate to it, and why were those the two films that were made. because they both had single individuals people could relate to. And Particle Fever could exist as an ensemble piece because it was, I mean, in a sense, we were freed a little bit because everybody realized that that was happening. But I think in fiction and narratives and story, it's actually much harder to...
You need a protagonist.
You need a protagonist. You know, in some sense, Particle Fever had a protagonist. It was the machine, you know, and everybody else was the supporting players. But generally, you know, to get a film made in particular, and I think probably with fiction novels and things like that too, you need a protagonist, and that lends itself to a single person, even though in actuality it's rarely the case that one person did everything.
I love the question, and I think that it's important to note that it's not just about science education and science communication. I think, you know, when I think about the way we talk about and the way we view on big screen what the civil rights movement was about, you know, which was of course this massive movement of millions of people. But when we tell the stories of the civil rights movement, we pick out individual people in the same way. I'd like to think we're moving away from that a little bit. I think that Carol Dweck's work talking about you know, growth mindset versus fixed mindset is getting us away from thinking about so many things as being sort of genius moments or just about some sort of innate talent. And we're moving toward sort of the work of it. And even in the movie industry, you know, there's a movie coming out later this year or maybe next year.
Hidden Figures.
Yeah, about the African American women who were instrumental in doing the calculations that got us to the moon. And that's a story that's been dying to be told for a long time. And finally, that's going to make it to the big screen.
Yeah, by the way, the book just came out last week and highly recommended.
You've already read it?
Yes.
Oh, wow.
Yeah.
Yeah. That's great. Cool. Somebody back here.
Oh, sorry. Hi. Sorry. So I know there are a lot of different approaches one can take when solving a math or science problem, but how do you as professors choose among those methods to help communicate with students who are having difficulty? And also my second question is, there are a lot of students who have interest in science and math, but struggle in one area more so than the other. So what advice would you give to them to encourage them to continue their interest and pursue the subject they're interested in despite having difficulty in the other?
Okay, can we go back to the first one before the mic goes away? So can you repeat the first one? It's you're curious about how these folks pick a strategy to communicate an idea.
Right, given there are so many methods out there to approach various math and science problems.
Sounds like a Dave question.
Dave will happily answer that question.
I think a lot about like who the audience is and what would hook them, and you know, when it comes to a calculus class, I always want to know who in my calculus class is coming at that from a biology perspective, who's coming at it from an econ perspective. Different things will hook them, will get them interested in taking a derivative. You can take a derivative in lots of different fields. It's important in different fields, but what will make it interesting to you depends on you, right? And so I need to get to know you a little bit and figure out what motivates you before I can figure out what the hook is for you. But I think you also have to figure that out for when you're dealing with an audience which is remote and you don't get to know them in person.
Yeah.
And so you have to figure out, you know, for this audience, what is going to be motivational to them, and then you just have to do a lot of thinking about and learning about what that audience is, and thinking about which audience you're going to try to reach with that particular piece. Did you want to add something?
I don't think I have much to add.
And part two was sort of a modified version of that, where how do you deal with particular students who struggle in a particular area? Yeah.
They may be interested in science but struggle with math, and they're kind of similar in terms of for students who want to major in science, they have to have some math background.
Right.
Yeah. I mean, I think the growth mindset thing that Dave was talking about, this idea that you know, we have this notion culturally that there are math people, using your specific example of math, and this goes very much with a fixed mindset where you have some amount of math knowledge, math talent, and you either have it or you don't. And I think the most important thing is helping people understand that they can grow. Like if you keep practicing it, you can get better at it. just like playing tennis or violin or any of these other skills that you don't expect to be a great tennis player the first few times you go out there and try it, but you know that if you keep practicing, you will get better at it.
I think also the fact is a lot of people don't realize the scope of science. And so there is this perception that you need to be good in math and science. And that's because a lot of people don't realize, what you can be doing that is science. And so in particular, again, I'll look at this woman, Monica Dunford, in particle fever. She's an experimentalist, and she's very clear. She says she was not good in math and, book science and things like that. And then she worked in a lab one summer. She didn't even know this existed, where you're building things. And you do use some, but it's a completely different emphasis. And it sort of opened up her world, because she knew she was interested in science, but she might have been intimidated if she thought she had to do theoretical physics or something like that. But again, it's something people aren't exposed to. So I think one thing is to just broaden your perspective on what can be science. I mean, if you're not so good in math, well, there's plenty of things that are scientific that don't need specific math things that you're working out. And similarly with other aspects of it, I think. So I think it's just looking at the larger field can allow you to, every discipline of science doesn't need the same skills.
And I think we need to, as a society and as individuals, really think about reframing the way we think about failure and struggle as negatives, and reframe that as failure and struggle are what propel us forward. Struggle is what we do so that we learn better, we learn things better. Failure is just another opportunity to sort of like, oh, well, that's the end of my knowledge, and I'm going to try to push it forward. And if we're thinking about that as from the perspective of we can do better, then failure is that. It's an opportunity. In my household, I'm working on this. Our daughter is 5 years old, Ellie. You might have seen her running around campus. And if anybody's in the house and says like, oh, I can't do that, she'll correct them, and she'll say, in our house, we don't say, I can't do that. We say, I can't do that yet. And we need to think that way about more of the world in which we live in.
Great.
Was there one?
Yeah, right here. Yeah.
Is this on?
Yeah.
Okay. So, Evelyn, there is a big contrast between you and Mark in that you are mainly a writer and Mark is a filmmaker. What do you think is one of the ways that makes your writing more exciting? I mean, if you see one of Mark's films on Netflix, you're going to be like, oh, that seems interesting, I'm going to look at it. But if you're just browsing the internet, you're going to see hundreds of stories. What captivates the audience for writing? What do you feel helps?
Yeah, so I will say that since becoming a writer, I have become so much more forgiving of clickbait titles. So the thing about clickbait titles is they get people to click. And so I don't title my pieces things like, lose belly fat with this one weird tip, but I try to title my pieces with true things that are related to what I am writing about. But finding good titles is a huge, it's a real struggle, I think, for most writers. Hopefully it's not just me. But, really a good title and the early things, finding a way to hook people either with story or with surprises, or some sort of unexpected contrast. One of my more popular articles that I've done is called The Saddest Thing I Know About the Integers. And it's about the fact that you can't tune pianos because 3 is not divisible by 2. And going into a little bit of the mathematics of frequency and pitches and how, why is the fact that 3 is not divisible by 2 relevant to tuning a piano? And so I think that has, it's got this emotional pull in it. It's a sad thing about numbers, and that's a contrast people aren't really familiar with. And then in the first paragraph, talking about music and math, and I think that's something that gets people to want to learn more about that. But really putting exciting things at the beginning is a big thing, and it's really hard. There is almost an infinite amount of things that people could be paying attention to instead of you.
So I'm assuming that means that a lot of your mathematics also relies on your music.
I write occasionally about that. It is that example happens to be that, but yeah, I wouldn't say it's a large proportion. Yeah.
So this sort of specifically pertains to particle fever. There was a lot of philosophical questions that were posed and related to physics. How important do you think it is, like, asking these big, like, philosophical and humanities questions with science in, like, science communication? I hope that made sense.
I mean, I think it's the big philosophical questions that motivate us to do everything, really. I think that, you know, you see all these physicists. I mean, it's a lot of hard work. It's a lot of drudgery day in and day out. And most of the time, they don't have the luxury of thinking about the big questions because they have, you know, a circuit that's not working, or they have some piece that didn't fit right, or on the theoretical side, you know, they have an equation that they can't solve or something. That's not fun at all. You know, I mean, they're tearing their hair out, but you know, what is ultimately driving them, and I think, you know, they have to come back to ultimately is what are the big questions that we're trying to solve, and we're all trying to, and that's what I think, you know, the reason particle fever did find a certain amount of success is because there are a lot of people that ultimately do wonder, where did we come from, and how did we get here, you know, what is the process? And those are the big questions that motivate you. I mean, that's, I think, almost any scientist, I think, probably originally got into it because they were curious about big questions. And the trick is to maintain that enthusiasm. In fact, actually, the Savastimopoulos, the Greek philosopher in our film, who's the one that has, you know, he's been working on these things for 30 years, and he had a great line, and he said that's, going from failure to failure with undiminished enthusiasm is the secret to success. I think that's really true. And the other thing he said, which relates to it, is that like the Odyssey, you have to also enjoy the process. So there is a goal, and that's the big things. But to be successful, you have to enjoy the process. And as he said, in the Odyssey, it actually wasn't even all that great when Odysseus got there. So it's better that he enjoyed the process.
Any more questions? Got one over here.
Dr. Kung, earlier you were talking a little bit about your work with the great courses. And how some of the little things I had, like keep your points to 6 minutes. Could you speak to a few more of the kind of the things I think about when putting together presentations for that, and why do you think they work well?
One of the things the great courses does that we don't have the luxury of in academia is they do a fair amount of field testing. And so my first course was about math and music, and the title that it ended up being was How Music and Mathematics Relate, which that's about as far from clickbait as you get. I mean, I just thought that was the most boring title, and I proposed, I don't know, a dozen other ones. But it's not like there's just somebody in an office saying, you know, that's a good title. You know, what they do is they survey their customers, and thousands of customers, you know, choosing one over the other later. The title is How Music and Mathematics Relate. And so they have some advantages that we don't. But when you get into actually writing these lectures, they're very good about helping you take whatever content you want and sort of honing it down in ways that do some of what we've been talking about. Like, they know their audience fairly well. They can help you figure out what a good hook is to get them into that particular content. They can give you a sense of of how long you can get through, and how there's always some boring material, and how much of that is necessary for the content, and how much is too much before you'll lose people. So they do a lot of that. They also help you a lot with things that I now think about that I never did. One of the things they're working on, it's in a studio, right? So it's a multi-million-dollar studio, and you have 3 cameras to work with, and you are constantly moving. And if you stay on one camera for more than about a minute, they are not very happy at all. And just this idea, I mean, it's something that we in academia are not very good at. 4 of us have been sitting here for over an hour.
Yeah,
and
tethered.
Tethered, we're actually tethered. But if I just walk around a little bit, it's more interesting to you because you have to move your eyes, right? And so just little things like that are things that you can use in the classroom, and you can use in lots of different places, ways of keeping things interesting for people. There's also all of these little things. I hope many of you taking a first-year seminar working on oral presentation, everybody has their word that's a go-to word for them, whether it's or like or something else. Everybody has their go-to word. And speaking on stage in front of people, speaking on a film, none of that. It's not a natural thing to get rid of that word, whatever it is for you. You have to work at it. And so I've now had a lot of practice getting rid of the ums. And when I fall back on them, there was somebody there to remind me. So that was incredibly useful.
Can I ask a follow-up question about that to Evelyn? How does that translate to the written page? How do you do things like crosscuts or keeping your points less than 6 minutes long in a medium which doesn't translate well to visual or oral cues?
Yeah, well, in some ways, I've got more luxury because people can choose to read it at the speed that they want, and they can go back if they miss the word or something like that. I really try to think, when I write a lot of blog posts, and I basically want people to come away with one idea. What is the one idea I want them to have with this? If they wanted a textbook, they would go read a textbook. They're reading this instead, and what is one neat mathematical idea that they can leave with? And then when I'm writing, how does this paragraph help me get to that goal? What is the sub idea in here that people will come away with? I do try to put in a few Easter eggs for people with more math background or who are interested in going deeper. So I don't try to take away every little bit of extraneous information, but I try to really hone that and say sometimes, well, I don't have room to talk about both this and this. So what is really the meat of what I'm trying to get people to come away from this with?
That's interesting. You both have talked about omission, basically, of what gets left out, in order to focus the reader. Yeah.
Yeah, well, and luckily for me, what gets left out can be a new blog post of its own if it's a fun idea that I like. Right. You probably can't have an outtakes reel for.
Yeah, well, I would need outtake libraries.
Yeah.
Right. There were so many stories, that we had to drop. And again, it gets back to this story. There was a young couple that they were married. Well, actually they weren't married at the beginning. They became married. So it was a man and a woman. They were both theorists. But they thought at this time that it's a big experiment going on. Maybe we should try to be experimentalists while, this is a unique time in the history of science. And it was a really interesting story. It was not easy for them. There was resistance, there was resentment. They ended up coming up with their own little experiment, which could be done at Jefferson Lab, actually down here in Virginia Beach. That when the LHC exploded and was down, they came up with this sort of 5 and dime model, idea of an experiment, and they became the spokespersons for it. They became the ones leading it. And it was this whole interesting story about that. They ended up getting married. And once the Higgs was discovered, we had to drop them. So, that's its own film, basically. And that was really it. It really was its own film. And we had to drop it. It just wasn't the one that was really the story we were trying to tell.
That's tough. In my spring science writing class, we read a piece by John McPhee, the New Yorker writer, called Omission, and it's all about the stories that he, it's all about what to leave out, and he tells a story to illustrate that. It's really fantastic.
Yeah. I mean, it's sort of interesting to think of the notion of omission in an age when people think they should be saying everything.
Right.
So it's sort of not, and it points to the fact what's going to be remembered of all of this, actually.
Right, right. What is the one thing?
Right.
Yeah. We have time for a few more questions. Got one over here.
Hi. How has the growing influence of social media over the past few years either helped or hurt your own personal endeavors to communicate science or math?
I love social media. I am pretty active on Twitter, and there's, I think, a pretty fun math Twitter community, and it gives me the chance to think I'm funny and make all these math jokes and stuff. So I really like doing that. But something I think is great about it, from the point of view of someone, I'm a writer, but I have also been in academia, and kind of helping people have positive experiences with math is one of the things that I really want to do. And I think there's a great interaction between professors, recreational mathematicians, parents, and high school teachers, middle school teachers on Twitter that I think doesn't happen in person hardly at all. And often there's this hierarchy and professional powers imbalance between people at different stages of math or different places in the math communication world. And I think on Twitter, you make a few jokes, you ask people for recommendations for classroom materials or things like this, and I think it can be a really democratic or a level playing field in some ways that people who wouldn't normally feel comfortable talking to each other can. I really enjoy chatting about math on Twitter and making jokes and stuff.
Just to be clear, you are actually funny.
Sometimes.
I think one thing that we haven't really discussed up here is that I feel like it's an incredible privilege to be in a position where I have the opportunity to communicate these things that I absolutely love. I love mathematics, and the chance to communicate that to a wider audience is just a absolutely wonderful thing. When I do the math, because I'm a mathematician, I might teach 3,000 or 4,000 students in an entire career here at St. Mary's, and I've reached many times that in a matter of a couple of years through these video lectures. And I think if we went back 20 years ago, it would just be the end of that. Like, that product would go out. And now I hear back from people. We were talking about this. Your movie's been out, Particle Viewer's been out for a while, but you hear back from people now regularly. And I get those emails from random people around the world. I was really compelled by this. Thank you for sharing that. And having it, I can have that dialogue now with people who are far away, and I absolutely love that.
Yeah, I think there's no doubt. It's a boon to being able to get the communication out there. I mean, that people wouldn't know about it. And there are these communities, these niche communities. I think the other side of that, and I'm not arguing for that, is the fact that it is difficult to stand out. So, we have a tremendous opportunity, but there's a lot of noise out there. And there's not really critical discernment of what's the good and the bad. And so, in fact, in particular, with the whole story of the LHC, there was this, paranoia initially that supposedly when the LHC turned on, it could have created a black hole that would have destroyed the universe. And this got a tremendous amount of play. Well, it turns out it was one high school science teacher in Hawaii. He didn't even know there's physics behind it. And he got it out there, and it took off on the internet, and it became this worldwide phenomena. And, it becomes almost impossible to control it, actually. So that's the other side of it.
That's definitely true.
That it would be nice if there was some way for some people to say, you know what, this is bullshit, you know. This is actually, but here we want everybody to know about this one. But it can get, you know, you can't control it really. I mean, you get the good with the bad actually.
Yeah, I mean, that's something that I think a lot of science writers, you know, the epic takedown piece is a very, it can feel satisfying to write something like that. This person is so wrong, and you know, I think there's a tension between like counteracting with just putting something that isn't sucky out there, versus, you know, tearing into somebody else's work. That's something that, you know, occasionally I write things about how somebody else is wrong on the internet, but in general I'm trying to say, well, at least, you know, I can hopefully make something good that has some integrity and people will find that, but it doesn't always get as much play as the cruddy thing somebody else did.
Yeah, the universe being destroyed by this black hole, that got a lot of attention.
No,
that got a lot of attention. Yeah.
Totally.
Yeah. Well, you know, when we were trying to sell the film, I mean, not really finishing it, but, you know, just trying to raise money and talking about it, you know, we avoided that because, you know, we didn't want to publicize it. But of course, if I was telling somebody about, you know, this big hadron collider, this thing, and they said, is that the thing about the black hole? And that became the way, yeah, we're making the film about the thing that does the black hole. Yeah. Oh, yeah, I want to hear about that.
One more?
So, Dave and like you guys, you all write like great pieces and that interest many people into science or math. And I was just wondering if there's anybody who is like special to you, you know, who made like something that got you interested into math learning or like their work personally.
There are long lists, I'm sure, for all of us. Martin Gardner did absolutely wonderful work popularizing mathematics. But sort of from a more modern perspective, I mean, I think the gold standard right now for science communication has to be Neil deGrasse Tyson and his ability to get out there and explain really difficult things in incredibly simple, catching ways. And I think that's just, it's absolutely wonderful to watch and see exactly how he does that.
Yeah, I actually...
With humor, too.
What?
He's funny. He does it with humor.
Yeah.
Mm-hmm. Yeah, I think I'm one of the only math writers who I don't even know if I've read anything by Martin Gardner. I know that he's very famous for being really great at this, and that's just not somebody that I encountered on my way to doing this. Yeah, what got me interested in math was one class that I took in college that really changed my attitude about math. It's that one professor who did it. I think a lot of people have that story about the one person who sparked their interest in that. But I mean, I think it's a pretty standard story for me.
I mean, yeah, I don't know if you were asking about our interest in science or in terms of how we do the storytelling, but the science story was similar to me for Evelyn. I mean, where I had a physics professor in college, and he just completely changed my perception of it. And I actually had been in a pre-med program. I had started in that, and I decided to take the physics major's physics class. And I'm just, you know, this guy, I still remember the first day of lecture, and he just takes this big book and he throws it across and says, we don't care about the books because here you're going to think. And I thought, that sounds good to me. And I did it. And, you know, a lot of people ask, well, why did I leave physics? And I think, again, this gets back to the fact that I saw lots of parallels, and what I really sort of discovered in film another way to deal with these issues of how do we represent the world. It's all about, in a sense, it's about us sort of trying to make sense of the world. And you can use the language of mathematics and science, but I think you can use music, and you can use images, you can use moving images, and that's the thing that really drafted me, and I wanted to move it on a bigger palette, I would say. But it's still the same motivation as trying to make sense of the world and, you know, our place in it.
Okay. Well, I want to thank our panelists for coming out tonight and thank you all as well for coming. So. Great.